Hi guys, haven't made a video in a while, but someone asked me today to make a video on this, so I decided to get right to it. Today I will be doing a video on completing the square. Now in this video I will be showing you how to get from things like this, x squared plus 6x plus 3, into their completed the square form, which looks like this for this example, x plus 3 all squared minus 6. Now you may be wondering, why would you want to get an equation like this, and I'm probably going to have to cover that in a different video, the reasons why we do complete the square. But for now I'm just going to cover how to complete the square, how to get, if we generalise this, how to get quadratic equations that look like that, ax squared plus bx plus c, which you may recognise, into their completed the square form, which looks like this, where d and e are constants, just as a, b and c are. Okay? For the this is the form we're trying to get things to. Now for the meantime we're going to look at examples where a equals 1, because when a is 1 it makes everything easier. So we'll do I'll do an example where a equals 1 first. So if a equals 1, we can rewrite this as x squared plus bx plus c. And this is what we're going to work for now, and later on I'll show you how to add in when a isn't necessarily 1. So the first first thing I'm going to do is I'm going to work this through algebraically and show you how the algebra works to get a unified formula. And then I'll show you how to do it just going through numerically, which is what I prefer to do when I'm given one of these questions in an exam. So the first thing we need to do is isolate the x squared and the x term from the constant c. And we'll see why in a minute. Now, the first thing you need to do is you need to make a mental leap and look at x plus half b all squared. Now some of you might be confused as to why I've written this, but some of you may notice the link between those. But for those of you that don't, I'm going to show you the significance of this. So if we write it out like this, and collect like terms, multiply out the brackets, that's half bx plus half bx plus x squared, and then this is half times a half is a quarter, times b squared is a quarter of b squared. And what we're going to do here is write it out like this. Actually, I'll do this on the page. Is x plus half b squared equals, right, in order, we'll do x squared plus, now half bx plus half bx equals a whole bx plus bx plus a quarter of b squared. Now, if we look at this here, we've got it, but we've also got this extra bit over here. So what we need to do is subtract this from both sides of this equation. So x plus half b all squared minus a quarter of b squared equals, because we subtracted this from this side too, equals that. And we can now put this back into the equation we got here. So we can say that x squared plus bx plus c is equal to, because we can write this part like that, so we've got x plus half b squared minus a quarter of b squared plus c. And with a little bit of rearrangement we can write it like this. Now this may look very confusing, and I'll give it to you, it is, but we have just completed the square algebraically, because if we say that d from over here is half b and e is c minus a quarter of b squared, then we have got here x plus d squared plus e, which is the form for completing the square. So what we have just done there is we have algebraically completed the square. Now, to take an example, if we were to take x squared plus 6x plus 3, as we have over here, and use this formula that we've got here, we'll end, if we write, so b is 6 and c is 3, because b is what goes for the x and c is the constant at the end, we can write this as x plus 6 over 2, so it's half of b, squared plus 3 minus 1/4 of b squared, and since b is 6, that is 36, 6 squared. This then write this again, sorry. 6 over 2 is 3, squared plus 3 minus and 1/4 of 36 is 9. This here is minus 6, 3 minus 9. So we can write that out as minus 6, which is what I got. So that's right. So that is using this formula, how to solve it. Now, as I mentioned earlier, I don't like doing this in exams because, well, if you memorize this formula, then all you have to do is plug in the numbers and like solve it through. But if, like me, you find it difficult remembering complex formulas like this, then if you kind of remember how I got there, but you can apply it numerically. So if we start with our example, and the first step, remember, is to isolate the bits with the x in it. And remember that leap that we had to make to get half of b. So x plus 3 squared, and we can write that out as x squared plus 6x plus 9, pardon me. But we don't want the plus 9, so we're going to do a little bit of subtracting from both sides. And now put this into what we had there, x plus 3 squared minus 9 plus 3, and that equals x plus 3 squared minus 6, which is what we got there. Now this method, as long as you remember the steps, so you isolate the x, you take half of the value before x, then you need to get it so it's in rearrange it so you can put it back into the equation and solve these two bits together. That is the method that I use for getting a completed the square version. Now, the only thing you may be pondering now is what happens when a isn't 1. Because remember, right at the start, I said for now we're just doing examples where a equals 1. This makes things easy. But now we're going to look at when a doesn't necessarily equal 1. So you've got ax squared plus bx plus c, and the only difference is we need to not get rid of a, but remove a temporarily. So we can write this as a lots of x squared plus b over a x plus c of a, and this multiplies out because that times that is ax squared, that times that, the a's cancel, so it's bx, and that times that, the a's cancel, so it's c. So you can write it like that. And now this bit here looks quite similar to what we have here, except wherever we have b, we now have b over a. Wherever we have c, we now have c over a. So we can use the formula that we got here again, but whenever we have b, we now use b over a instead. So we can write it out, and wherever we have c, we now have c over a minus 1/4 of b over a squared. Now, the first step is to kind of simplify these a bit. So you end up with x plus, now if you're multiplying fractions, you multiply the top by the top, b, and the bottom by the bottom, 2a, squared plus c over a minus, now this b over a squared is b squared over a squared, and then timesing top you get b squared over 4a squared. Now, this looks very confusing, and it's not quite the format we want. However, it doesn't take too much more rearrangement. If you now put a in front of each individual bit, some of you might already see where we can simplify here, but I'll just explain. We've taken bits out, but here there's a common denominator of a throughout the whole of this bracket, and we've got a multiplier of a, so the a's can cancel, so we can end up with a lots of x plus b over 2a squared plus c minus b squared over 4a, and that here is the completed formula. Now, if you're wondering where these two kind of match, well, if we consider a equals 1, so that just becomes normal. 2 times 1 is 2, so that looks very similar because b over 2 is the same as half b. And c minus b squared over 4a, if a equals 1, that's b squared over 4, which is the same as a quarter of b squared. So that is the full formula for if you want to do it algebraically. However, as always, I mentioned that I don't massively like having to work through the algebra and then putting in the numbers, though you can put in numbers for this one and it works. But I'm just going to work through an example numerically, like I did with the x squared plus 6x plus 3, just to show you how you can do that as well. Okay, so the first step is we need to get, I'll use the example 2x squared plus 4x minus 8. So first you need to define the terms. A equals 2, b equals 4, and c equals minus 8. So this is just me showing you through how we can use this formula first, briefly. So 2 lots of x plus 4 over 2 times 2 squared plus minus 8 minus 4 squared over 4 times 2. So all we've done is put in the values of that to this, and solve that. 2 lots of x plus, now 2 times 2 is 4, 4 over 4 is 1 squared, plus, and then in here we've got minus 8, and then 16 divided by 8 is 2, so we've got minus 2, and this is minus 10, so we can write out this like that, and that is the square formula. However, you might not, like me, you don't necessarily like getting this formula and then putting the values in, so we'll do it step by step. So first thing, write it out again, is we need to take a out of the equation. Since a is 2, we can write this as 2 lots of x squared, so divide each bit by 2, 2x minus 4. Okay, so that makes 2x squared, 4x, and minus 8. So multiplies out. Now remember, we need to take this bit, okay, and half it and put it in a bracket. So we'll do x plus 1 squared, solve that out, plus 2x plus 1, and then subtract the 1 because we don't want that, equals x squared plus 2x. Now put this back into there because it's equal. So 2 lots of x plus 1 squared minus 1 minus 4, which equals 2 lots of x plus 1 squared minus 5. And if we multiply out this, we end up with 2 lots of x plus 1 squared minus, and then 2 lots of 5 is 10, which is the same as what we got here. So just to summarise, what I've shown you in this video is I've shown you the algebraic way of completing the square, and then how you can then substitute in values to get the answer, and also how you can solve it step by step but with numbers instead, which personally I find a lot easier. So if I was given complete the square for this equation, those are the steps that I would follow. Okay, and that would likely, pretty sure, get you full method marks on an exam, and that's the complete square formula that you want at the end. As I said at the beginning, I might post soon a video why this completed the square formula is useful. It's like why getting x plus, getting it to look like that. I mean, sometimes I've got to mention, sometimes you've got an extra bit at the beginning, like in this case here, and sometimes you don't, like this case here. probably show you at a later point why it's useful to complete square. But for now, I hope you learned something, and thanks for watching. Bye.